Thank you. Can you hear me? Yeah. So, all right. Thank you, Jim, for the introduction. So, as Jim said, I'm Alvaro Muñoz, also known as Pond Tester in social network, Twitter, GitHub, and so on. I work as a principal security researcher with Fortify team. I mainly do static analysis, related research, and probably, well, I focus on web application security, right? What I find more interesting is getting remote code execution on web applications, and I have responsibly reported critical remote code execution vulnerabilities to companies like Microsoft, Oracle, Workday, Salesforce, and so on. So one of them in Microsoft I will be sharing with you today, hopefully, if we have time. So apart from that, I have some experience around deserialization. I started not in 2015 when, as Jim said, but actually in 2012, playing with XML decoder and XStream, trying to get remote code execution in RESTful web services, right? So we were able to get remote code execution in some libraries like RESTlet and RESTEasy. And then I moved into the binary format of Java deserialization, right? And I found, to my knowledge, is the first remote code execution gadget for Java deserialization for the binary format back in 2013. And it was not in Apache Commons collection, but actually in the Spring libraries, right? So unfortunately, this gadget didn't become as popular as the Apache Commons collection gadget became. And I'm saying unfortunately because we all saw that this was like a tipping point, right? And when Chris Verhoeven and Gabriel Lorenz found this gadget, the community started looking for these vulnerabilities, they started fixing them, and so on. So we could have saved ourselves like a couple of years by starting back in 2013 or even before. So at this point in 2015, Chris Verhoeven and Gabriel Lorenz published the Apache Commons collection gadget, and everything changes, right? All the researchers start looking into Java deserialization. They start publishing vulnerabilities like in WebLogic, WebSphere, and many other applications. So I retook my interest in Java deserialization. I found like a technique to bypass what is known as the look-ahead object deserialization. That is like the standard mitigation technique for this kind of attacks in Java. And also I found like multiple gadgets leading to remote code execution, including one in the Java runtime itself, so not requiring any third-party libraries in order to work. So then I switched gears and started looking into JSON to close the circle, right? So from XML to binary and then to JSON. And I published some approaches to get remote code execution in JSON deserializers back in last year in Black Hat and DEF CON. So most of this is Java, right? And this is what is known as the Java deserialization apocalypse. And I think, well, it's bad because, I mean, there was many applications that were affected by these bugs. But in the other hand, it was good because we got this category all together to go into the OWASP top 10, right? And we, as a security community, we have knowledge about the latest trends and latest categories like, I don't know, SPL injection or JNDI injection. But developers don't normally have this visibility in what vulnerabilities they should focus on. And I think that having a secure deserialization in the OWASP top 10 is a good thing in order for developers to start looking and fixing these vulnerabilities. So at that point, I decided to take a look into .NET because, well, I'm not a .NET developer, I'm not a .NET researcher, but since I had some previous experience with deserialization, I decided to take a look because apparently, there was a previous research around .NET deserialization, but there was no remote code execution gadget. And as happened with Java before, it was not until a remote code execution gadget was published that the community started fixing and taking care of these vulnerabilities. So I decided to look for one in order to start, the ball moving. So what I'm going to present today is the result of this research. So I will first introduce a brief introduction into serialization. Then we will be reviewing what are the most common .NET serializers and formatters. And then we will move to the more like builder and defender part of the talk, that is finding vulnerabilities and fixing them. All right, so Marshall in pickles. I will be using Rick and Morty picture because why not? So this is Rick, right? He's an instance, an object living in the VM. And at some point, the developer wants to take Rick out of the VM, right? So he wants to put it in the file system or into the database or send it across the network. So he put a rig across the magic portal, and then he gets a pickle rig. So at a later stage, we want to recover the object back in the VM, so we will put pickle rig back into the magic portal and then recover and reconstruct rig again. All right, so there is one thing in this slide that is critical for these deserialization attacks to work. So anyone? Something that is like the design flow of all these formats, like Dev? So say that again, sorry.
The deserialization string will go to the client and come back often. So there's an attack surface that's going to be used.
Yeah, well, this is just a very simplified model of deserialization. But the issue I was referring to is that we're not sending just the pickle itself, but we're sending a pickle rig with the serialized data as well. So this is what is known as the type discriminator. And basically, if you're familiar with Java deserialization, even though it's a binary format, you will find like class names or type names in the serialized data. Same thing with .NET, for example. This is JSON.NET. You will find some dollar attributes, dollar type attributes containing something that looks like .NET type and .NET assembly names. So if the attacker can control the type discriminator and they change pickle rig with a pickle Morty, then the server will blindly trust that and then will instantiate an instance of Morty instead of the rig one, right? So there is probably nothing really dangerous here because they are going to invoke the default constructor of this Morty class, which is, it takes no parameters, so there is nothing where the attacker can modify the behavior of this and just get arbitrary code execution. However, apart from the default constructor, there will be other methods that will get invoked. Like, for example, in Java, we'll get the read object and read resolve methods. And in .NET, the same thing. We'll have like this deserialization constructor over here, deserialization callbacks, even some annotations that we can use to annotate methods that are going to be invoked by the framework in order to fully reconstruct the object, right? Same thing with XML and JSON. These libraries will normally just invoke the default constructor and then invoke setters in order to populate the data in the class types. And they will be invoking setters in order to do that. All right, so all that the attackers need to do is find a gadget, right? And a gadget is nothing else than a type or a class that is sitting in the target application class path. So they cannot provide the implementation for the type. They can only provide the type name. And since they can control the values for these properties of this class, then they are able to actually modify the behavior of the methods that are going to be invoked, like, for example, the deserialization callbacks or the setters. So this is more like a builder and defender talk, and I'm not going to focus on how to find find gadgets leading to remote code execution. But I think it's good to show you an example of a very simple one leading to remote code execution so you can have like an idea of how they look like. So this is a system Windows data, object data provider. It's a type in the Windows GAG, so it's available without any third-party dependencies required. And it contains 3 different setters, right, that will initiate some invocations that will end up invoking this method over here. And here we are basically just using reflection to invoke a method name on an object instance passing some parameters, right? And those are exactly the ones that we can control if we can control the values that are passed to the setters, right? So if an attacker provides a piece of JSON.NET data like this one to a vulnerable endpoint, the vulnerable endpoint will basically instantiate the object data provider, and it will invoke the setters for the object instance, for the method parameters, and for the method name. And as we saw before, this will initiate these calls here, and will end up invoking the reflection and getting the, in this case, the calculator to pop up. Right, so I'm not going to talk more about gadgets. If you want to check which gadgets are available for Java, visit the YSOCerial project. If you want to know more about gadgets in .NET, I wrote this project that is called whysocial.net that basically it can be used to generate payloads and gadgets for different formats in the .NET family. So this is a simple example. For example, just invoke it like the one that we just saw. If you want to attack JSON.NET, just specify the formatter, specify the gadget, specify the command, and it will generate the payload for you to use in your penetration test and POCs and so on. So with that, let's move into reviewing what formatters and serializers are vulnerable in the .NET family. So as I said, this is nothing new. Back in 2012, James Forso from the Google Project Zero was already presenting on how passing untrusted data to a binary formatter or net data contract serializers could lead into some malicious code being run. At that time, there was no remote code execution gadget, and I think that he only presented a gadget that was able to delete files from the file system or initiate some SMB relay attacks. Right, so as happened with Java before, since there were no remote code execution gadgets, no one paid really attention to these vulnerabilities, and there were like many vulnerabilities related with .NET deserialization until last year, probably. So last year in 2017, my colleague Alexander Muñoz and myself, we found a remote code execution gadget in .NET, and that was followed by James Forso presenting two more, so there are like a number of them right now. So as we said, James presented a couple of formatters that are vulnerable in their default configuration. Those are binary formatter and net data contract serializer, but there are more, right? These are the ones, like I said, that are vulnerable in their default configuration. They should never be used with untrusted data, at least in this default configuration. And they include the binary formatter one, that is the one that James presented, but this one is also used internally by other serializers, right? For example, this binary message formatter is used by the Microsoft message queue system, so if you can send them arbitrary types, you will be able to get arbitrary code execution. Same thing with the object state formatter, that is used by the ASP.NET view state, so if you can change the view state and survive the HMAC verification, that will also lead to remote code execution, and we will see more about this later. So then we have more like sub-formatters using web services, FastJSON, SweetJSON. Those are like third-party libraries. So the most popular and used one is the binary formatter. And this is probably the most common anti-pattern that I found. I literally found like thousands of applications in Shodan vulnerable to remote code execution because they were using exactly this pattern. And this is this is very simple. They are basically instantiating the binary formatter and then serializing some data, base64 encoding that data and putting that into a cookie. So if that cookie comes back, the server is going to deserialize that, and since there is no HMAC verification, it will go in and run arbitrary commands using these gadgets. So the first time that I found that was in App Harbor. Anyone knows App Harbor? Yeah, I know you use it. So while browsing the site, I realized that they were setting this cookie with this AAE, that is nothing else than the magic number for the binary formatter and then base64 encoded. So that means that this site that is basically like Heroku for .NET applications, like to host .NET applications, was vulnerable to remote code execution. We reported that, and they fixed it. But then we realized that they even had a blog post explaining how to do exactly what they were doing. So instead of keeping some objects in the server side, just save some memory and put them in the client side by serializing them and putting them into a cookie. So we tell them about this blog post, and they now deleted this blog post. However, this same advice is everywhere. You can find like multiple GISTs and blog posts, and even in Microsoft ASP.NET MVC framework was using the very same approach that they silently removed back in 2013, right? And this is related with what Jeremy was talking before. Like if they don't publish like a CVE, you don't know that there is something that you should update and so on. Like, this is kind of important. So let's see a demo. This is a vulnerability that I found in Azure. Yeah, so this is from last year. So as you can see, even though this research by James Forso was published in 2012, there were many developers even Microsoft developers using binary formatter with untrusted data. So if you're familiar with Azure Active Directory or application proxy, you basically have your intranet here, and you have your web application that you want to share, right, to expose to your remote employees. So your employees will basically connect to the application proxy, then will be redirected to the Azure Active Directory, where they will be like asked for the credentials that will be checked against your own instance of the Active Directory, and then they will be returning a token and then authenticating against the application proxy. I think that is better explained with a video. So this is, we're visiting an application that I'm exposing through this Azure application proxy, and I'm redirected to the Microsoft single sign-on, right? I don't even need to log in into Azure because this is a pre-authentication remote code execution. So I will basically send the request through Burp or any proxy. And well, basically, I will just send this request to the repeater so we can see what is going on. And as you can see here, we get a 302 redirection to the single sign-on page in Microsoft, and then we get this cookie assigned here, right? If you recognize this magic number, the same one in App Harbor, this basically means remote code execution. So we just get, what we have to do now is generate our payload, and we will be basically, this was before I wrote the YSOCerial.net, so I had to do it by hand. But basically, I will be doing a DNS resolution against my own DNS server, and I will be leaking the computer name just to prove that the remote code execution was not in my own intranet servers, but actually in Azure servers. So with that, I will just generate the payload. During the process of generating the payload will get executed. So I will get a connection back to my DNS server from my own VM, as you can see here. So that's my VM computer name, so nothing interesting so far. But now, if we copy-paste the payload generated by our gadget or payload generator into the cookie, and we send this request to Microsoft or to Azure Network, we will see that we will get some connection back from different servers, actually, not just one. So for example, the first one is from this server down here, that is Microsoft servers, and then if I submit the request again, I will get a different connection, which means that I can compromise all the application proxies that are working like in a load balanced way, which means that I can intercept any traffic going to any intranet of customers using this Azure thing. So that was pretty bad. The good thing is that Microsoft only had to patch their own system, and that was quite easy, and they did it very quickly. All right, so apart from those deserializers that are vulnerable in their default configuration, there are other serializers that are known as template deserializers that work with an expected type, right? So if you want to deserialize something, they will only work with one type, right? For example, if you're expecting a shopping cart instance, then you cannot send like an object data provider payload because that won't work, right? So those examples of that is, for example, the data contract serializer, the data contract JSON serializer, and the XML serializer. So in these cases, they are still vulnerable, but the attacker needs to control not just the data that is going to be deserialized, but also the expected type. You may think that this is not very common, but I found that, for example, one good example in .NET Nuke, that is the most popular content management system in .NET. And basically, at some point, they were taking the contents of a cookie that was not signed, and that was like an XML cookie. I don't know why. But anyway, they were extracting some type name from this XML, and then they were invoking the constructor of the XML serializer with this data that can be controlled by the attacker. So now the attacker can control the expected type, and then it was extracting the rest of the XML and then deserializing that. So now the attacker can control the expected type and the data being deserialized, which means that the attacker can control the whole object graph and run arbitrary code in the server. So that was reported and was fixed. Okay, so the third group is those serializers that are vulnerable in some specific configuration, right? So those are, for example, JavaScript serializer, that is the native Microsoft JSON deserializer, and JSON.NET, that is the third-party one that is even more popular than the Microsoft one. So let's see the first one. This is JavaScript serializer. JavaScript serializer is safe to be used with untrusted data as long as you don't do this. That is basically passing a type resolver. If you use a type resolver, that means that it's going to include the type information along with the JSON data, and then it's going to process that type information. So it's going to allow the attackers to instantiate arbitrary types and invoke these setters that will lead to arbitrary code execution. Same thing with JSON.NET. But instead of an argument to the constructor, in this case, it's a property, right? And they are setting this type name handling, which means that it will include and process the type information in the JSON data. So you have to set known, because if you set objects, arrays, or auto, then the framework will be including this information, and it will make the endpoint vulnerable. All right, so how about finding if your applications are vulnerable? So there are like different approaches. The first one, probably the most simple one, is to inspect the traffic flowing in and out of your applications and look for magic numbers or these signatures of the traffic being serialized data. As we saw before, this AAE, AAAD is an example of this. This is the base64 format for the magic number of the binary formatter, but there are other magic numbers, like, for example, for the object state formatter or for the XML serializer, and there are other encodings. So I wrote this simple Bear plugin that you can freely use, and basically we'll check for these magic numbers in different encodings. So, well, I didn't meant to be like a perfect, very accurate plugin, so it will have some false positives, like, for example, if this magic number is found in some images, that will be reported. And also, it might find that you are sending serialized data, but it's not checking if there is a signature for that serialized data. So maybe you cannot exploit it. It's not a false positive because there is serialized data, but it's not exploitable. So we will see more about the view state later. So the second approach is an active approach where you are basically sending a payload and watching if that payload gets executed and trying to recognize out of band if that gets executed. So example of this is like, for example, making the server sleep for a number of seconds and then check if the response gets delayed. Or, for example, like I did with Azure, you can run a DNS lookup in order to, if you control the DNS server, to check if the payload is being executed. IAST is another approach. I don't know if it's passive, active, or something in the middle, but I consider it active because you have to actually instrument your virtual machines, right? So you instrument the virtual machines, you monitor what is going on inside of the virtual machine, and then if some untrusted data gets into these deserialized methods, then we will report that. That's good for pre-production, but not for production. Anyway, if you have access to the source code, that's probably the easiest approach. Just check if some tainted data, some untrusted data flows into one of these deserialized sinks. If you do that, you have to consider that it's not as simple. Well, for some formatters, like binary formatted, it's very simple. For some other formatters, such as XML serializer, you have to correlate different data flows and also taking control flow into account because there can be a serialization binder that we will see later. So you have to consider that. But this is something that most of the static analysis tool can do. So if you use Fortify, I know it worked because I wrote the support for that, so you are safe. Also, fixing vulnerable endpoints, right? So now you found that your application is vulnerable. Sorry. So how can you fix it, right? So the first approach is, do you really need to serialize that data? And this seems silly, but I found like many applications that were using serialization for strings, right? And one good case for this, one good example, is the Nancy web application framework. The Nancy is basically a web application framework that is very similar to Sinatra framework in Ruby. And they care about security, and they implemented CSRF protection, but instead of putting a unique token into the CSRF cookie, they were serializing that token into binary format serialized data and then putting that into the cookie. So making the whole framework and then all the applications built using this framework vulnerable to remote code execution because of this implementation of the CSRF protection. Same thing with type discriminators. JSON and XML is okay to use, but you should not use them with type information, right? So that was the case of the Breeze framework. Breeze is a .NET entity management framework. They basically expose, it's very similar to Spring Data REST, so they expose some database entities through our RESTful web service automatically. And they were sending the type information to the JavaScript clients. So that made no sense because JavaScript is not going to understand the .NET type, so they were not using that. So because of this mistake, the whole framework was vulnerable to remote code execution. And they fixed it very quickly in a matter of hours by just setting this type name handling setting to none, right? So this is actually the default value. So probably at some point they were playing with that and they changed that and they remain in the code. So I think it's a good idea to explicitly set these secure values explicitly and then even add a comment like, do not change this, please. So, okay, what if you really need to serialize data? So the first case was when you were serializing a string, so that was not required. Now, if you have some object graph that you want to persist in the client side, for example, for performance reasons or whatever reasons, then if you are not expecting the client to modify that data, then sign it and verify that the data hasn't been modified, right? If you do that, always use an HMAC and never use something like MD5 or SHA-1 with secret and data because that's vulnerable to hash length extension attacks. And this is the way that App Harbor and Azure actually fix their issues. They just sign the data that they were not expecting anyone to change, and then they verify that that change didn't get modified. Same thing with ASP.NET. If you remember, back in 2013, they removed this cookie temp data provider, and they replaced it with something else. And that was basically the same approach of serializing server-side data into the client side, but this time they were using the Data Protector API, right? They were doing something very similar to this, called the Data Protector API, protect the bytes, and that will basically sign and encrypt the data using the web config validation and encryption keys, and then this data won't be able to be tampered with without the server side noticing. So another good example of signing and verifying the data is the ASP.NET view state, right? So for those of you that are not familiar with a view state, it's like a representation of the state of a page. So the server is going to send you the state of the page to you as a hidden form field. And then when you submit the form back, you are submitting the previous state so the server can reconstruct the previous state and then continue from there. So this is used by ASP.NET. And I think that in the beginning, they were not even forcing, or they were not signing and encrypting the view state. So the problem back in these days was that if there was some sensitive data, for example, in the view state, then the clients were going to be able to extract and leak that data. Also, if the client was able to modify the data because it was not signed, then they could change the application logic. So that was back in the good days, like many years ago. And at some point in version 4.5.2, Microsoft even started ignoring the enable view state MAC, meaning that even if you set that to false, they will always encrypt and sign your view state, which is good. And they even backported that back to 1.1. So I was curious, and I ran a shutdown query, and I found that more than 200 servers are still running vulnerable versions that are not using any signature or encryption in the view state, which makes like a good cryptocurrency botnet or something like that. So, Anyway, at some point, they improved the cryptographic posture of the view state by actually using a key derivation function. And this was a very interesting approach because if the attacker is able to leak the validation and encryption key, then they will be able to actually change the encryption and change, well, not change the encryption, but changing the view state and then putting the payload there and get arbitrary code execution. So what they did is that they generate some per request unique strings that they call purposes. And what they do is that they run this through a key df, a key derivation function, in order to generate some keys that are unique for each request. Now, if the attacker is able to leak these encryption and validation keys, those keys won't be able to tamper and modify the view state because the ones that will be used are these ones over here, right? So I just, connected a debugger and took a look, and I visit the account register page, and then I check the values for these purposes strings. So the first one is primary purpose, right? And this one is always going to be the same, is this string over here with the client state, if it's for the view state, other values for other things. And then you have the specific purposes, right? So the first one is template source directory / account. The second one is account register ASPX. So both of them quite predictable for an attacker, right? The third one looks like pretty random generated, like this 776 EC whatever value that looks like arbitrary value. However, this is the same value that is used in your anti-cross-site request forgery token cookie, right? So the attacker is going to be able to read that, and is going to be able to generate all these strings, and therefore, if they are able to leak these keys, then they will be able to generate those keys, right? So now the problem is you have to be very careful with not leaking the keys. The first way that the attacker can actually leak the keys is if they find a file disclosure vulnerability in your application, like, for example, an XXC vulnerability. Also, there may be some vulnerabilities in the framework, like in 2010 and 15, that allow the attackers to actually leak those keys. From Troy's side, you may recognize this. Apparently, you can actually leak the validation key and the decryption key if you are not using custom errors, at least in the past. Also, I found like hundreds of validation and decryption keys in GitHub. So if you are going to install something like a CMS or a block just by cloning the repo from GitHub and then installing that, be very careful and always generate new keys. Never use the ones that are provided by these kind of projects. Same thing with one-click installers. You get the latest version of this whatever CMS or whatever block application, and then you install it, and some of them will use static keys that they won't generate per installation. In those cases, the attacker will be able to install the same CMS, for example, and then leak the keys and then attack and get arbitrary code execution in your CMS block application or whatever. So be very, very careful with leaking the key. A good advice is to encrypt some sections of your web config file. So you can actually ask IIS to encrypt these sections. So if you get like XXC vulnerability or a file disclosure vulnerability, at least they won't be able to leak those keys. So sign-in is OK if the client doesn't need to modify the data. So that's OK. But what if this is a pure client server that are sending arbitrary messages? Then you cannot sign the data, because in that case, the client needs to have the signature keys, the validation keys, which if the attacker is in control of the client, it makes no sense. So in this case, what you have to do is actually bind it, right? This is very simple. It's very similar to the concept of the look-ahead deserialization in Java. So basically, right before instantiating those types that are controlled by the attacker, just stop for a while and ask yourself if you want to really deserialize this assembly name and this type name, right? So you are provided with this assembly name and type name, and you can stop and apply a whitelist or a blacklist, and then decide if you want to continue with the deserialization or stop, right? So this is done by implementing the serialization binder interface. This is a good example by Jonathan Birch from Microsoft. Basically, just implement this interface and then prepare a list of allowed types, with the type names that you are going to allow, and then a preloaded instance of those types. This will be important. I will show you why later. Then just implement override the bind to type, and then check if the type that the attacker is sending is within the whitelist of allowed types. And if that's the case, then continue and return the preloaded type. Otherwise, just throw an exception and abort the deserialization. So then you have to actually instantiate the serialization binder, assign it to the binder property, and deserialize, right? Easy. So while I was reviewing some Microsoft products, I found one of them being vulnerable to remote code execution through deserialization. And they had a deserialization binder in place. So it was like, okay, they are caring about this. But then I realized that the serialization binder was not that secure as they thought, for example. So this is not the actual Microsoft code, but this is something that I put together in order to reproduce more or less what they were doing. So I'm still in the process of disclosing this vulnerability and haven't been fixed. So at some point, what they were doing is they were checking if the namespace starts with Microsoft dot put the name of a very popular Microsoft product here. And if that's the case, then load the type and return it. Otherwise, return null. So there are multiple vulnerabilities here. First of all, if you return null, it may not do what you may think that it's doing. It's not going to abort the deserialization. It's going to fall back to the default binder, which will bind anything, which will bind including the remote code execution gadget type, so it's not protecting anything. So the second problem here is that loading the type using reflection at deserialization time is very costly, and actually this will lead to DOS. The attacker can easily DOS your application because you are not using preloaded types. If you remember the good example from Jonathan, he was actually preloading the types here and then just returning them in the method that gets executed during the deserialization. And the third problem here is that this namespace here is just huge. It contains like thousands of types, right? So even if the attacker cannot find a remote code execution gadget within this Microsoft dot something namespace, they will be able, probably chances are that they will be able to find what is known as a bypass gadget. And what is a bypass gadget? It's just a gadget, so it starts with a deserialization callback. And at some point, instead of running arbitrary code, for example, or doing bad things, they just run a nested deserialization operation. The problem here is that even though you are protecting your outer deserialization operation, the inner one, the one that is run by this bypass gadget, has no binder in it, right? It's instantiated here and then just deserializing. There is no binder assignment. So that means that this deserialization operation will let all the remote code execution gadget types to be processed and deserialized and the payloads to be executed. So yeah, this is basically sum ups what I was talking to you about. Never return null because this will fall back to the default binder, and that's bad. Also, don't use reflection to load types at runtime because that will DOS your application. And the fourth approach is to replace it, right? So we saw the first one is stop using it if you don't need it. The second one, if the client doesn't need to change the data, then sign it and verify that. Third approach is if the client needs to actually send you data, then use a binder to control what types gets deserialized. And the fourth approach is if the architecture of your application allows you to do that, change these formats that include the type discriminators, the type information, change that with something else. And a good alternative here is Google protocol buffers, where you agree, the client and the server agree in what they are going to exchange, and then they exchange just the data. So if they are going to exchange an instance of a com.acme.user, then they will agree, they will know in advance that they are going to exchange that, and then they will just share the name of the user, the last name of the user, the address of the user, but no type information, no property type names, or nothing like that. And also, if you don't really need the type information, like we said before, just don't use it, and that will make those JSON and XML serializers to be safe, at least from this kind of attacks. So with that, mahalo. And if you have any questions, I think we have time, right, to take questions? Jim? Oh, sorry. Hmm? Yeah. Yeah. Yeah, so that's this approach, and basically the only cases where you really need to include type information that I can think of is if you are dealing with, for example, polymorphism types, where you may send, I don't know, an instance of an animal, but you need the information to know if you need to reconstruct a dog or a cat, for example. So you need to send information, the type information with that. And that's the whole purpose of all these type name handling things, the JSON, JavaScript script serializer, these simple type resolver, and so on. So those are meant to deal with some of the object-oriented programming features like polymorphism, generics, and so on. So if you should only be sending things like DTOs and POJOs, right? Something very simple. If you find yourself that you require things like polymorphism, then maybe you need to rethink what you're sending. Tim?
Alvaro, if Rick had a breakthrough, a therapeutic breakthrough at the end of Pickle Rick, remember therapy, why did he not change behavior in future episodes?
I don't know. Ask Rick. There you go. I love this slide, so I will just put it again. So yeah, this is the whole design flow in serialization is that they allow you to change the type discriminators. And if that happens, then attackers can arbitrarily instantiate any type, and that's the big problem here. Any questions? All right, so thank you.